Good morning. I will present the scientific article Generalized Integral Transforms and Kirchhoff's Transformation in Nonlinear Heat Conduction. Authors Josué Espinal, Emmanuel Macedo, Joao Quaresma, Renato Cota. The Generalized Integral Transform Technique (GTT) is combined with the Kirchhoff transformation in solving transient nonlinear heat conduction problems. Considering temperature dependence on both the thermal conductivity and the thermal capacitance. The hybrid methodology is employed with a convergence acceleration strategy based on a quasi-steady filtering scheme. The approach is demonstrated for a test case based on boundary condition of the second and first kinds. The results were critically compared against numerical data obtained using the methods of lines. The approach can be directly applied in the thermal analysis of nuclear fuel rods or plates, considering temperature-dependent thermophysical properties. This presentation will include an introduction, an analysis, test case, conclusions, and acknowledgments. The present work is motivated by the search of more precise and cost-effective simulation tools for nonlinear heat conduction problems, especially for computationally intensive tasks that require hundreds or thousands of evaluation of a specific formulation, such as optimization, inverse problem analysis, real-time simulation, machine learning, and simulation under uncertainty. Accounting for the temperature dependence of thermophysical properties becomes mandatory in various classes of materials under more extreme operational conditions. In such cases, the adoption of properties linearization approximations can lead to significant deviations of the simulation from the actual physical behavior. The thermal analysis of nuclear fuel rods provides a very relevant example of this class of problems, due to the very large temperature gradients achieved and the marked variation of physical properties within the typical wide temperature ranges. In light of the intrinsic limitation of classical analytical approaches in handling such class of nonlinear problems, an interesting alternative to the traditional time-consuming purely numerical methods is the advancement of hybrid numerical analytical methodologies that combine the accuracy, mild computational cost of analytical methods with the flexibility and generality more typical of numerical tools. One such hybrid approach is the so-called Generalized Integral Transform Technique, GTT. The formalism behind the GTT for nonlinear diffusion problems involves the choice of eigenvalue problem with linear coefficients, though arbitrarily variables in the space coordinates, that are characteristic representations of the original nonlinear coefficients, for instance, by evaluating them at the initial or steady states known temperature distribution. In addition, nonlinear heat conduction problems can be reformulated through the well-known Kirchhoff transformation, when the nonlinearity associated with the temperature-dependent thermal conductivity can be removed from the governing equation, and collapse to the nonlinear thermal capacitance, explicitly introducing the nonlinear thermal diffusivity in the new formulation. In terms of GTT methodology, it has been demonstrated that the combination of the integral transform approach with the Kirchhoff transformation can offer converged behavior, since the new diffusion term is exactly integral transform and the temperature dependence of the thermal diffusivity is much less pronounced than for the conductivity and capacitance independently. This work further explores the solution of nonlinear transient heat conduction by combining the GTT approach with the Kirchhoff transformation, by avoiding an implicit transform transient term, and in addition adopting an explicit quasi-steady filter for convergence acceleration. The proposed approach is demonstrated for a test case based on boundary condition of the second and first kind, considering temperature-dependent thermophysical properties. one-dimensional nonlinear transient heat conduction problem is here selected to illustrate the proposed approach with prescribed heat flux and the prescribed temperature at its boundary, given by equation 1 to 4. The dimensionless groups of equation 5 to 9 are introduced. Therefore, the dimensionless problem formulation is written as equation 10 to 13. Applying the Kirchhoff transformation on the dimensionless temperature, a new dependent variable is constructed as shown in equation 14. The dimensionless diffusion equation 10 and the boundary and initial conditions from 11 to 13 are then rewritten in this new variable u as shown in equation 16 to 19. To obtain the solution of the problem defined by the equations 16 to 19 through the Generalized Integral Transform Technique, an explicit quasi-steady filter is adopted that allows for the harmonization of the boundary conditions. The formulation of the filter problem U sub f is proposed as in equation 21 to 23. Analytically, solving equations 21 to 23, the expression for the filter becomes equation 24. The formulation for the filter potential U sub h is such that equation 25-28. To develop the solution of system 25 to 28 with homogeneous boundary conditions, the GITT methodology is applied, starting with the proposition of eigenfunction expansion basis. The eigenvalue problem is shown in equation 30 to 32. Solving the auxiliary problem of equation 30 to 32, it is just like the equation 33 to 35. Integral transform pairs are shown in equation 36-37. Integral transformation of the original problem is shown in equation 38. It then results the coupled system of ordinary differential equations for the transfer potentials of such equation. It is shown from equation 29 to 41. Table 1 illustrates the convergence behavior of GTT solution, where it is noted that the convergence rates for the dimensionless temperature are indeed satisfactory, requiring truncation orders at most around 10 to 15 terms for attaining 4 significant digits in the analyzed cases. Table 2 shows the convergence analysis of the dimensionless temperature using the methods of lines. For dimensionless times and position values, note that with around 15 to 20 mesh points, the results are already converged to 4 significant digits in the analyzed cases, agreeing with the GTT solution. Figure 1a and Figure 1b provide, respectively, the spatial distribution and time evolution of the dimensionless temperature, which are directly compared to the methods of lines results, with excellent agreement throughout the solution domain. The generalized integral transformation technique is applied in combination with the Kirchhoff transformation to solve transient nonlinear heat conduction problems, avoiding an implicit transform transient term and adopting a quasi-steady filter for convergence enhancement. A test case is considered and a convergence analysis of the proposed solution is presented, illustrating the enhancement promoted by the employed filter. Also, the hybrid solution is critically compared to a numerical solution by the methods of lines. With excellent agreement, this approach can be readily applied to the thermal analysis of nuclear fuel element with temperature-dependent thermophysical properties, aiming at the best possible convergence rates when considering time-consuming coupled neutronics and thermohydraulics. The authors are grateful for the partial financial support by CNPq and FAPER Brazil. Thank you very much.